Well, we're going to dive into our final sensor here for water detection. And that's a pretty important point when we're talking about ROVs. And as you'll see, it's a little bit more than just water detection. There are a few other things we can do with this. We're going to talk about our basic water sensor, how to build one. Go into water sensor connections, how to connect it up. Go into a little bit about software. One of the things about water that we are around, none of it is so pure that it's non-conductive. So we can take advantage of that, and that the water has some conductivity to it. The presence of salts and minerals and other types of chemicals will vary the conductivity in the water and lower its resistance. We'll be using the voltage divider circuit, much like we had in Module 6, with the fixed resistor on the top half of the voltage divider, and the probe will be the bottom half, and the probe will simulate the resistance on the bottom half of the voltage divider circuit. So if we have no water detected, the resistance between the probes will be close to infinity, and the Arduino will read 5 volts or 1023 counts. If you want to put some large number in there like 10 megohms in the voltage divider equation, you'll see how that works out. Now if we have a very small amount of water, resistance by the probes may drop to somewhere to 100 plus k ohms, 100, 150, 200 k ohms with a little bit of water. And as an example of that, with 100 k ohms in the bottom between the probes, the Arduino will read 4.5 volts or 930 counts. Now if the probes were saturated, completely covered with water, and it was a very conductive solution, the resistance of the probes may drop down as low as 100 ohms. And with 100 ohms between those probes, in the bottom part of the voltage divider circuit, the Arduino will read 0.5 volts or about 10 counts. So we've got a very sensitive and pretty sophisticated sensor here. Here's our connections. We have our 5 volt going through R1, which will be a 10 k ohm resistor. You can use any value of resistor here. I would say above 1k and below 100k. The higher you go, the more sensitive this circuit will be to water. I like 10k, it's a very nice balance. And you'll see on the bottom side of that resistor, the wire connects up to 81 or analog A1 input. And then the red wire I have going off to a water probe, and the brown wire is connected to ground and going off to the other probe. Now I make these probes out of simple paper clips. In the case we have a little bit of water between the probes, you can see over here the water at the very end of the probes. We may have the 100k or a little bit more resistance between the probes. It means we'll have less than 5 volts and less than 1023 counts. Now if we have lots of water, we're going to have less than a volt there and less than 200 counts, because we're going to have less than 2 k ohms resistance between the probes. So you can use this not only for a water detection, but also water level. So I built my probe out of a couple of paper clips, and I went ahead and did them really crude so you could see they didn't have to be anything fancy. I just opened them up real quick and pushed them into the ends of the jumper wires we have that have the sockets. So I used a set of sockets on one end and pins on the other. Here's my whole setup. You can see up at the top, the 100 k ohm resistor is connected up to the 5 volt bus. The other side of that resistor is connected to the red jumper wire and the yellow jumper wire. The yellow jumper wire then goes over and plugs into A1 on the Arduino. Now we have a speaker here. So what good is it to have an alarm without a speaker to sound? And the minus symbol on the speaker gets connected to ground, and the S as in speaker, gets connected to pin 8 on the Arduino. One of the things over here on the right, I referred to the resistor side A and side B. Resistors have two sides. They can be swapped, but pick one, call it side A, and then the other one will be side B. You can pick it up and swap it around. It won't make any difference, but at least as far as referring, if I tell you side B has a red wire and an Arduino pin, you'll know what I'm talking about there. Now here's the connections. Again, go through the connections here. Provided that there's a little schematic of it. Now, selecting the speaker, you have two devices that look identical in your kit. The speaker has a plus on it, and the plus is away from the pins. You can see the plus right here, and it's on the side opposite to the pins. The buzzer has also a plus with a circle on it, but it's on the side closer to the pins, and it also has the letters HSD stamped at the top. Do not use the buzzer, use the speaker. The speaker is shown here on the left and on the bottom. Do not use the buzzer. So as far as the software, copy M9 metal and do a save as M9-water. You'll create an 8 sample average. You'll calculate the difference from a set point. I put 1000 as my set point, or my alarm set point. Anything below 1000 would sound an alarm. Next, compare the sample against the alarm set point. If your sample is below that set point, sound the alarm. And if it's below the set point, do a serial print with the text alarm and a space. And after the alarm loop, you're going to serial print both the sample value and the difference values. Regardless of whether it's an alarm or a normal, you'll be sending out the values. And then you repeat that loop forever. Now, how to sound the alarm. There's a little bit of code I wrote, and up at the top I created two constants, freak L and freak high, 250 and 100. The higher the number is, the lower the frequency will be. So 100 is a higher frequency and 250 is a lower frequency. It's just the way it works out, because we're working with time here and not frequency. And if you remember, frequency is the reciprocal of time. So if we drop in here to the first part, we're going to start the low frequency sound. And we're going to turn it on, put the alarm output to high. We'll delay the number of microseconds specified in the constant freak low. In this case, it'll be 250 microseconds. Then we'll put the output low. And again, we'll delay that same number of microseconds. And then we'll loop on there for a number of counts called alarm delay. We'll talk about that in a moment. After we do that, we're going to go turn on the high frequency sound. So we're going to have a two-tone alarm here, and it'll go back and forth, and believe me, you'll hear it, and after a while it'll get a little annoying if you keep it running, but you'll figure out how to turn it off. So the same thing with the high frequency sound. We'll go through the same little for loop, and for the number of times of alarm delay. And while we're still in the loop, we'll print out alarm. That last bracket down there is the end of the alarm loop, and we're here printing out sensor counts with a comma and diff counts. In this, I'm introducing two new commands, delay microseconds and print ln. Delay microseconds is just as it sounds. You'll delay the number of microseconds there as opposed to milliseconds. And print ln will print the value followed by a new line command. Before, when we did that, we did a print with a /n, a \n, which did a new line. The print ln is a little cleaner, and it takes care of that new line for you. The alarm delay value is created by taking your sample counts, dividing it by 5. So as that sample value gets closer and closer to 0, your alarm delay will get closer and closer to 0. So if you have, say, 1,000 divided by 5, we're going to start off with an alarm delay of 200. And as we get smaller and smaller of our counts that we've read, the alarm delay will get shorter and shorter, which will result in a faster and faster repetition rate between the high and the low frequency sounds. Now, once you have this all working, there are some things you can do with it. You can calibrate it and use it as a conductivity sensor for measuring different types of fluids. You can also calibrate it and use it for a level sensor of the level of fluid in a container. And finally, you can use it to build an electronics housing water detector. You can wrap the probes with tissue paper, sprinkling some salt in there as you go. Wrap a probe with a few layers of tissue. Keep sprinkling salt. Then once you have the probe with a few layers of tissue paper around it, go and wrap the other probe with a few layers of tissue, again sprinkling salt as you go. And then wrap the two probes together, sprinkling salt. Now, as long as those tissues remain dry, the salt won't dissolve and everything will be fine. You won't have any connection between the two. Now, if you go and tape the bottom and the top of those probes to the bottom of your electronics housing, leaving the middle of those probes fully exposed, of course they're still wrapped in tissue paper, but if any water gets into the system, it'll be sucked up by the tissue paper. The moisture in the tissue paper will melt the salt and make sure that it starts conducting. So you can work in very non-conductive water, and by putting the salt in there, it'll ensure that you have conductivity and detect the water very fast. In the next video, you can see me running my probe through different types of water. I think I used reverse osmosis water, tap water, pool water, and the pool water is from a saltwater pool, and then finally water that's been saturated with salt. You can hear the difference between each of the different types of fluids and the depth extended into the fluid.